Hello everyone, my name is Richard Watkins. I'm from the Centre for Architecture, Sustainable Environment at the University of Kent in southeast England. And I'm going to talk about the efficacy of an earth tube from long-term measurements. I'll start off by looking at the building which is served by the earth tube, and then talk about the earth tube a little bit, and then look at just a few of the main results. So the building is located in southeast England, just north of Dover, right on the coast. It's a sloping hill here by the water, about 200 meters away. And the building is in two round buildings, 1 story and 2 stories joined together. The earth tube intake is here in a little garden, rather disguised with a sculpture, and the path of the air, the earth tube goes down 1.5 meters or so and around underneath the garden into a plant room. So let's look at the earth tube in a bit more detail. The earth tube is 16 meters long, 0.6 meter diameter, made of concrete, 100 millimeters thick and about 1.5 meters down. The fan that drives it is very efficient, an ECM motor, DC, and the air goes down through this intake here, which is normally covered. There's an insect screen down into the ground, and there's the pipe, the start of the earth tube proper. It goes along the earth tube, which is 0.6 of a meter diameter there, so one can crawl along there to the end to inspect sensors and so on, but there's no space to turn around. One has to reverse out all the way. At the other end is the fan, shown there, or in more detail here. We can see it through the window here because this is used for educational reasons. People can see the fan. The air goes from the fan into this heat exchanger here. The air is passed through these narrow glass tubes, and outgoing air from the building is passed across on the other side. So, to some of the results. This is quarter-hourly data for 6 years, and this has been analysed in some detail. So looking at the cooling power or heating power, what do we find? The x-axis here goes from May 2013 by year up to March 2019, and heating is above this line and cooling below this line. The y-axis is the cooling power in watts, or heating power in watts. Straight away one can see that there's more time spent in the heating mode than the cooling mode, and in fact it's 70% of the time the earth tube was heating, 30% cooling. This did surprise me. I thought earth tubes were mostly for cooling, and the heating or preheating of air really wasn't very important, but I was wrong. And in terms of energy rather than power, we can see over 6 years we've got 6 megawatt hours of energy for heating and 1 megawatt hour for cooling. So a very big difference, about 5-to-1 ratio, or 6-to-1. In looking at monthly data, the earth tube heats incoming external air in every month of the year, even in the summer. We can see here, this is January to December. These are average results for each month over the 6 years. So as heating in the summer is more or less the same the power as the cooling in the summer, very similar, which is probably reflects cool mornings or cool nighttime air. So let's look at we expect the heating cooling power to increase as the difference between the air in temperature and the earth tube temperature increases, and this is what we find here. Increasing temperature of the air entering the tube, we find that we have a transition from heating to cooling. It's not a straight line, there's a lot of scatter, and this suggests there are other things taking place. And a notable one will be the fact that the earth tube's internal temperature is probably not stable. So we can look at that by looking at the transition temperature, which is when the earth tube is air coming into the earth tube exits with the same temperature. And if it's any warmer, it'll be cooled, and if it's any cooler, it'll be heated. That's the transition temperature. This looks at the 6 years data, monthly, January to December again here, and we see the incoming transition temperature here goes from in the winter, January, February, around about 9 degrees up to 18 degrees almost here. So there's a very big difference in the temperature there, which is responsible for a lot of that scatter. And one of the big things about the earth tube, it moderates the incoming air, of course. Temperature of the incoming air is moderated by the earth tube, as shown in the frequency distribution of air in and air out, just looking at the summertime of June, July, August. So we have the frequency distribution, our frequency on the y-axis, and we have the air temperature on the x-axis. The blue line shows the distribution of air coming into the earth tube, and the red line for the air exiting the earth tube. And you can see this is constricted. The outgoing air has a lesser range than the incoming air, significantly 2 or 3 degrees on either side. So this is very helpful. The earth tube acts as external thermal mass in effect. So those are the main findings. Passive heating, about 1 megawatt hour per year. Passive cooling, a fifth of this, much larger than the energy used by the fan. The transition temperature varies from 9 to 18 over the year, and it's very effective in moderating temperature of fresh air entering the building. Thank you very much for listening.